Well, hello. So this talk is about program extraction, and more precisely about proof-producing synthesis of ML from higher-order logic. So program extraction, what's that? So everyone knows that you can define functions in theorem provers. So you go around defining functions, and you can prove properties of them. And then, but if you then view these functions as a functional program, then you might want to take them out into the real world of Haskell or ML or so forth to get fast execution or have them as standalone things. So the current approach to that, sort of common approach, is to do program extraction. What this means is you essentially take the function and print it into the syntax of the external language. So even in this, so this is getting more and more common. For instance, the most famous example of this would be concert, where the entire compiler was written in Coq and then extracted out. So all of these extraction mechanisms don't currently give you that much guarantees, and they sort of assume that the semantics of the logic matches the semantics of the language you're mapping into. So in my naive translation here, you could question, is the semantics of plus here really the same as the semantics there? So depends on your functional language, does it have big numbers? So this is a sort of shortcoming that has been known for a long time. I mean, John Harrison, who's famous in the theorem proving community, he calls this a glaring leap of faith, this gap. So that's where our contribution comes. So we try to reduce this glaring leap of faith by essentially doing more work inside the theorem prover. So the users can go on defining their functions exactly the same way as they did, prove the same sort of properties, but our contribution is to have new automation inside the theorem prover, which does this translation inside the prover, and proves essentially that the generated, in this case ML code, indeed implements the logic function, and proves this with respect to an operational semantics that lives also inside this logic. So now we have the syntax of ML here, and just transferring that outside of the theorem prover is not as big a step. And I should mention that this comes at no extra cost to the user of the existing program extraction, because this is all automatic and it can deal with the same kind of programs. Okay, so this talk is about translating whole functions into a mini-ML code and prove that, and have this live inside the theorem prover and prove that it indeed does exactly that. Everything lives inside the prover until the very last step. Okay, so what's the source like? So it's higher order logic in my case, so that's Church's simple theory of types with polymorphism. Just think of this as the lambda calculus with ML-like types. So features are that every function is total. They can be recursive. You have type variables, you have functions with first-class values, pattern matching, user-defined data types. These are, of course, not immediately in lambda calculus, but you build on top of various existing infrastructure that gives you essentially that. Also, there's partially specified functions. So this is a subtle point. They're not partial functions. There's partially specified functions. I'll mention a little bit more about that later, but not much. So what's the target language? In our case, it's mini-ML. So this is written by my co-author, Scott Owens. So it's his idea of the simplest ML-like language that remains nice to programming. So it currently is purely functional, has mutually recursive data types and functions, pattern matching, higher order functions, polymorphism, not LED polymorphism, but HOL-like polymorphism, arbitrary size integers, no modules, no record types, and no tuples I could add, but you can do that with the data types. The semantics, we have big step and small step. We prove that they correspond both to when they terminate, the values correspond, and they also agree on when programs don't terminate. So in order to prove things about the semantics and to do the translation, I'll make all the statement in terms of eval. So eval says that an expression, if eval is true, then the expression evaluates in the environment using the big step operational semantics to evaluate v for which the post condition is true for v. So this, that's the operational semantics, and I should mention that it's deterministic, for otherwise this might not have the intended meaning. Okay, so let's make a few basic statements, translation. So given some mini-ML for the value 2, we can relate this to the whole value of 2 using a refinement invariant. So this takes two arguments. The first one is the whole int, and the other one is a deeply embedded value from the mini-ML semantics that relates those. It says true or false if they're related. You can state that the mini-ML variable with the name n in this environment holds the integer value held in whole variable name n as that, and you can get compound expressions like n plus 2 as follows. So the core idea behind the algorithm is that you perform these derivations of eval theorems in a bottom-up manner. So you start, for instance, at the leaf. You could have 2 there, so that's just a theorem on its own. You can have n, which in this case, this is just a statement saying that n is bound to an integer in the environment. So we assume this on the other side of the theorem. So this is the assumptions, that's the conclusion of the theorem. And then we can combine these with various rules for plus, and then you get this, and the assumption just clings on the other side. Okay? So then you can move the assumption over, and once you've done this, you have it in a form where you can introduce a lambda. So you can produce a lambda in the whole world, so this is a normal lambda in whole, and on this side you get a closure in ML, and the invariant is now a little bit more complicated. So it tells you that this is a closure that, given an int, produces an int that is exactly that. Okay, so I'll give the definition of this. Given two refinement invariants and a function, and given a closure, evaluation of that closure with any v which satisfies the invariant A will result in a u that satisfies the function, computes the same result. So with these definitions you get nice properties. It's sort of composition is very natural, it's almost like tab checking. So if the refinement invariants match, then you can, of f of x, then you can get applications of f to x, both in the mini-ML and the logic. And as I explained, you have rules for doing the same with lambdas, so you can introduce lambdas in the mini-ML. Okay, so what about type variables? So I've shown you how integers, if you have an integer in whole, that's how you can state it with eval. But with if the type variable is an alpha, then I leave this as a variable as well. This is a normal whole variable. It has the type, the same type as int, essentially, except you have an alpha where there would be a z there otherwise. So with this, you could either instantiate alpha immediately, or you can keep it through your computations as normal. So for instance, if we have twice defined in whole as follows, then it would derive twice in mini-ML, and you'd get a refinement invariant, all stated in terms of this A as a refinement invariant. And then you can of course instantiate it if you apply twice to, for instance, the functions we've had throughout, then you get it instantiated, both the constant and the variables, the types instantiated. So what about recursion? So if we apply the same bottom-up approach to derive a mini-ML function for this, then we get into a problem because we don't know how to deal with this. We don't have any specification that fits. So the solution is here to note that every whole function is total, and to admit a function you have to prove termination. From these termination proofs you get induction principles, that follow the shape of the function, the logic function, very closely. So now we'll try to use this. So we perform the bottom-up derivation as before, and at the point where we find GCD, the constant GCD in the logic function, we use this theorem, which of course is trivial because the left-hand side is the same as the right-hand side. But once you start instantiating these, then of course this will just be an assumption that sort of moves along. So I should mention that these EQ here are just to restrict on what values this is allowed to be applied. So this one is allowed to apply, this statement only makes sense if the argument to GCD is exactly n, and here m mod n. For all other values, it's vacuously true. Okay? So if we do the bottom-up derivation with that, we get something, it's a little bit verbose, but for the case, recursive case, you get this assumption where the arguments are exactly the same that goes into the recursive call, and in the conclusion you get just the variables. And this matches now the induction scheme, and you get something like this. For every m and n, you get exactly those. You can essentially delete that assumption using the induction that we got. And now we have m and n. We can push those for alls essentially inside, and these disappear, and you get exactly the result that we had for the non-recursive. I should mention I skipped some details here, particularly how to deal with these, and you can find that in the paper. So, at a glance, the algorithm is to derive in bottom-up eval theorems of this shape. You get the derived code generated there. You have f, the function you're trying to translate, and you get some assumptions. And you get rid of these assumptions using the induction that arises from the user's proof termination for f. I should also mention that partially specified functions leave some assumptions here, so they can sort of survive this, and then the user gets that. So I should also mention that MiniML and the HOL-to-MiniML translation initially only knows about int and bool and functions. However, whenever it sees a new user-defined data type, it automatically generates lemmas that it can use to produce the constructors and pattern matching for that. That's one way it can extend its original sort of setup. Another way is that the user can provide new refinement invariants. So the user can, for instance, use int to define his own nat with just define the refinement invariant and then prove like add and subtract and so forth, match. And we've done such extensions for natural numbers, n-bit words, finite sets, maps, and so forth. And so the design was always to not be any different for users from the current ways of extracting functions. So this was, so the user would not need to change his libraries at all, or to change the way he does define his functions. So this results in us being able to apply our tool to various functions that already exist in the library of HOL, just to see if they translate. And these are some of the examples. Some of them are quite sizable, like parser generator. Yeah. And then we also tried some from Okasaki's book. Some of these had interesting data types in them. So, in summary, we've added automatic procedures for producing these translations, program extraction translations inside the logic, and that way given more trust to the code extraction at no extra cost to the user. Also, I should mention that we go to MiniML, and of course, we're not entirely sure whether this is really a proper subset of some other ML. So what we're currently working on is something that goes underneath. So a verified implementation of MiniML so that we have like a full stack, a full sort of flow out of HOL, so that if you prove things about your functions, you can extract them and run them on a verified system.